Right, what I thought I will do is just to do some, start with some math revision for you guys, just so that you can hopefully see where the equations we're talking about come from. So I'll just run quickly over these. Hello. I don't know. Right. So let's talk about the gradient, the divergence, the curl, and Laplacian. I'm sure you did this in maths, but just good revision just to relate it in more specifically to fluid mechanics. So if we start with the delta operator, or the del, the nabla, the first thing you need to know is that this is a vector operator. So in 3D, that's just defined as kind of upside down triangle, which is the partial derivative by the x times I plus delta dyj delta dzk, right? So it's obviously a vector operator. It's a vector itself. Now, why we need this? Because we will use it on functions, whether they are vector fields or scalar fields. So if we start with a scalar field f, that could be anything. Now we can define something called the gradient of f, or grad f. Well, how do we do that? That's just the gradient of f equals, in terms of delta, that's just delta f. So it's equal to the partial derivative of x with respect to, the partial derivative of f with respect to x times I plus the f dyj times plus the f dzk. So what you guys can see already, that the gradient of f, although f is a scalar field, i.e. is just values, that has no direction, if you take the gradient of that, it actually gives you a vector, as you can see. So this is a vector, all right? So the gradient of a scalar field is a vector. Right, and what it means really, as you guys can see, the partial derivative is just the same idea as normal derivative. So dx is basically how much f is changing in the x direction. The f dy is how much f is changing in the y, and so forth. So it's the local derivative of a function with respect to a spatial direction at a given point. Okay. So if you like, is is basically the derivative in vector form. So that was the gradient. The next one is the divergence. So if we have a vector field v, probably it shows that on purpose, but so v in 3 dimensions has components u, v, s, small v, and w. Then the divergence of a vector field, we can only have a divergence of a vector field, is defined using the delta operator. That's why we introduced delta in the beginning. So divergence of v is basically the dot product of the delta and the vector field v. And of course, what do you guys think you will get if you take the vector, the dot product? Do you get a vector or a scalar? Scalar, yeah. So that's just simply the u dx plus dv dy plus dw dz. Okay. So basically, the components of v, partial derivatives of those with respect to the spatial directions. Okay. More importantly to us, if we assume that v is itself a velocity vector field. So that's what's of importance to us in aerodynamics, that v itself is the velocity field. And let's also assume that the flow is incompressible, meaning density is constant. So if that's the case, we get the following, is that the divergence of v, where the v is the velocity field, incompressible flow actually gives you 0. Actually, this is what I told you last time. That equation is the same as the conservation of mass, or the continuity equation for an incompressible fluid. So next time you open a textbook and you see that equation, where v is the velocity field, that's basically is the mass conservation. Okay, that's what mass conservation is. So in 2D, where if we take the v has 2 components, u and little v, okay, then the conservation of mass, or the continuity equation, which is basically that, which is must be equal to 0, of course, by this definition. In terms of components, if we just think about the divergence in 2D, we ignore dw dz, and we take u and v and put those equal to 0. So again, when you see this equation next time in the textbook, du dx plus dv dy, that's actually just the conservation of mass in 2D for incompressible fluid. Very important to remember, it has to be incompressible fluid. Right, so let's talk about the curl of a velocity field, of a vector field. Again, I'm using v in 3D. So this is a vector, and I'm taking the curl of that. And the curl of that is simply just another name for the cross product of two vectors. But in this case, it's defined in terms of the delta. So you take the delta times by the velocity field v, and of course the the cross product in 3D. It's a little horrible, but it's really based on the idea of the determinant in a matrix form. So if you want the first one, basically the way to remember is you cross, if you want this one, okay, so you cross this and that, and you take those components. If you go into the j, then you cross that, and you only consider those and so forth. So I'll just show you what I mean. So this is how it's written. Remember here the change in signs, because it starts positive, change the sign, goes back positive as well. But anyway, this is just purely mathematics. But what you guys see is that the result, of course, of a cross product is also a vector. So you get a vector field out of that. Now, as I did with the divergence, for us as aerospace engineers, aerodynamics, is we want v, if we say that v is the velocity vector field of my flow, this is what we can do. So if v is the velocity field in a flow, and if we take the curl of v, which is the velocity field, okay, that gives us what I told you last time as the vorticity vector. So the curl of v is just the vorticity. And remember, vorticity tells you something about the rotationality of the flow. So if the vorticity is non-zero, there is some rotational flow within the flow field. But we can make the assumption, or sometimes we can actually make the assumption that the flow is irrotational. What that really means is just the delta times v is 0, or vorticity is 0, because delta times v is vorticity. So in 2D, so if you take the cross product of delta times v, or the curl of v, to be 0 because it's irrotational, then really that simply reduces to this equation here, dv dx minus du dy equal to 0. So again, next time you see this in textbook and is equal to 0 in 2D, that is just the vorticity being 0. All right, that's just saying the vorticity is 0, i.e. your flow is irrotational. So that's it. That's in 2D. The vorticity vector is just dv dx minus du dy. Any questions so far? Right. So let's talk about Laplacian. So the Laplacian of scalar field phi, and by the way, I'm just using phi. I know we spoke about phi being the velocity potential last week, but this is just in general. So the Laplacian of a scalar field phi is defined as delta squared phi, which is really nothing but the divergence of delta times the gradient of phi. It's basically the divergence of the gradient, which really is the second order partial derivative of phi. Okay, so that's what it is. So it's written as, and remember that the dot product gives you a scalar function, and is in this case, because it's a Laplacian, it's just second order partial derivative. So delta squared phi by the x squared plus the rest. So delta squared is called the Laplacian. Sometimes you might see it as written as a triangle, proper triangle, but it's probably easier to remember as delta squared, or the Laplace operator. Okay, so let's link this to aerodynamics as well. So in aerodynamics, a potential flow which has a velocity field v, because it's a potential flow, I told you last week that we can derive that velocity field from a velocity potential function phi. Okay, so in a potential flow, the velocity field can be derived from a velocity potential phi. And this velocity potential phi actually turns out if the flow is potential flow satisfies the Laplace equation, i.e. the delta squared of that velocity potential phi is actually equal to 0. And that's the Laplace equation. Which if you think in terms of this one is just that sum. If you take that sum in 3D and put it equal to 0, that's saying that phi satisfies the Laplace equation. So in 2D, with the velocity vector v components u and small v, okay, and we are saying, what I told you last week, that the velocity components u and v can be related to the velocity potential phi. Anyone remembers the simple equations? What's u equals in terms of phi? And what's v equals in terms of phi? Anyone? Any guesses? Okay, so that's the component. So the component, the x component of the velocity vector v, u, that's just the partial derivative of this potential function phi in the direction x. And the component v of the velocity is just the partial derivative of phi with respect to y. Okay? So, any function which satisfies the Laplace equation delta squared phi equal to 0 is said to be harmonic. Okay? Now, the other thing we need to know about Laplace equation is that it's actually linear. There are no non-linear terms. Okay? And obviously linear are easy to solve. They make things easy for us mathematically. Non-linear terms, for example, like 1 over x, that's not linear, is it? Or, x, for example, y equal xy or something, so that's not linear. So, oops. And because it's a linear equation, this Laplace equation is linear, this leads to a very important property of the Laplacian equation, which is basically we can add solutions together, and when we add them, the result is satisfies the Laplace equation itself, which means it's a solution to the Laplace equation when you add two solutions that satisfy the Laplace equation themselves. Right, what you guys hopefully will see is that the Laplace equation written in this form is actually, there is no time in it. Okay, it's purely defined in terms of space, not in terms of time. So it's purely spatial quantity. You guys can see there's no partial derivative with respect to time. Which means, in real life, okay, we can actually say that the Laplace equation can be used to describe steady flow conditions, because in steady flow conditions there is no variation with time. The d phi or d phi dt is 0, and therefore d squared phi dt squared is also 0, and that's why we only have the spatial derivatives here. So it just means we can actually say that Laplace equation models, or can be used to model, realistic steady flow situations like steady flow around an airfoil, or maybe a cylinder, or maybe steady heat conduction. That's another one, but that's heat. So that's the main thing. Okay, let's keep going. Okay, the Cauchy Riemann equations and how these relate to potential flow. So, have you done this in maths yet, or not yet? Okay. That's why I thought last week. I wasn't sure after the lectures, like, have they actually seen it? But if you haven't done it yet, you should be able to see it in year 2 in maths. So the Cauchy Riemann equations, how do they arise, and why they are important? Okay, we start with the following, saying, if I have a complex function f of z, where z of course is the complex variable, which is generally is just x plus I times y, where I is the imaginary number, of course. So if we have a function which is a function of z, and is the components of that function is u plus iv. For now, I don't want you guys to think about u and v as the velocity components. That's just, you know, a term in the x direction. U, that's the real part, and v is the imaginary part. You don't have to relate them to the velocity components. Okay. So I have this function here, which is obviously a complex function. So what mathematicians tell us is that you can actually make a simple test through partial derivatives to tell us whether this complex function f of z is analytic, means you can differentiate it everywhere or at a given point. So that's what analytic means. So you can define it at a given point, or maybe in general at every point. So how do you do that? So the Cauchy Riemann equations actually tells you that. So if you satisfy the Cauchy Riemann equations for the function f of z, you can say that the function f of z is analytic and differentiable at a given point. Let's say that point is z equal to z0. So that means f of z is analytic at a given point only and only if the following two equations are satisfied. And these are the Cauchy Riemann equations. So if we say that the partial derivative of u by x is dv dy, and at the same time the u dy might equal minus dv dx. If you satisfy these two equations for any function f of z, that function is called analytic or differentiable, okay, at a given point. And as I said, in general, you want it differentiable over the regional space and maybe over the whole space. So you guys can see these Cauchy Riemann equations tells you something about the function. So what we can say that if the Cauchy Riemann equations are valid, means they are true, then the function is, as I said, analytic, and vice versa. Means that if the function is analytic, then the Cauchy Riemann equations are true. Okay? So that's your test. Get the Cauchy Riemann equations, that tells you something about the function. Very quick example just to show you that. So if I take f of z to be the complex number itself squared, okay, which in terms of x and y, that's just x squared minus y squared plus 2ixy. I hope you guys remember this from maths. Then by comparison, we know that fz is u plus iy. So if you compare this equation to that, clearly, I hope you guys can see that u is just x squared minus squared, and v, which is multiplied by I, is 2xy. So that's your real number for f, and that's the imaginary number for, or the imaginary part for f. So now let's do the Cauchy Riemann equation. So let's take du dx and compare it to dv dy, and take du dy, compare it to the minus of dv dx. Right, I need volunteers now. Anyone tell me what's du dx? Come on guys, quickly. 2x, very good. Right, so what about dv dy? 2x? So is this correct? Yeah, very good. So let's go to the other one. Du dy? Minus 2y, very good. And what about dv dx? No. dv dx is 2x, and you put the minus. So du dy, which is minus 2y, then is minus dv dx. So definitely the Cauchy Riemann equations are satisfied in this case. So what we can say about this function f of z, z squared, is definitely analytic or differentiable everywhere. Okay, how this relates to potential flow when I mentioned psi and phi last week. So I'll just talk about that, and hopefully you guys see the link. So the Cauchy Riemann equations in potential flow. So the main thing to remember in potential flow, we have these two wonderful functions, the phi and psi. The phi being the velocity potential, and psi being the stream function. Clearly, out of them, I can actually just make up a function w of z, which is the same as fz before, which is actually the real part is the phi and the imaginary part is psi. And of course, the complex number is always z equal x plus iy. That's always true. So we ask the question, is this function analytic? Or does it, or what are the Cauchy Riemann equations we can come up with? Now, what we know from last week is that the velocity components u and v for a velocity field are related to phi and psi in the following way. So we said that u is d phi dx. So this is the velocity component in terms of phi, so u and v. The next line will show you u and v in terms of psi, the stream function. Okay? So from here, what guys can you tell me? What can you conclude anything? What's the conclusion? Conrad. I'll have to pick up on you. By the way, I've seen you in some brochures in the news. So you guys did some Euro quad Cyrock. Yeah, well done. That's very good. Yeah. I'm trying to praise you, mate. Anyone? Come on, guys. What can you conclude from those? It's not difficult. Huh? Why? So you jumped. Okay. But keep it simple. U is equal to that and U equal to that. So d phi dx is equal to that. And d phi dy is equal to minus d psi dx. So, which you're right. So, which are actually the Cauchy Riemann equations. So, by inspection, you can say that. And these are actually really Cauchy Riemann equations for the function w, which is phi plus I psi. I hope you guys can see that. So, if you understood the last slide, you can see this is really true. So, therefore, this function w, the complex potential, we can call it, out of phi and psi, is analytic. So it satisfies the Cauchy Riemann equations. Right. Any questions before I stop on this?